So in this video, we are looking at problem 5. It says, because of your knowledge in physics, you have been asked to investigate a train wreck between a fast-moving passenger train and a slow freight train. Two different trains, two objects, and they're both going in the same direction. And you have statements from the engineer of each train and the station master, as well as some measurements you made. And so you have to check the consistency of the description of events leading up to the collision. And so you decide to calculate the distance from the station the collision should have occurred if everyone's statements were accurate. You're verifying that what everyone said was true. And if it wasn't, now you're going to get a different distance than 0.5 miles. So if you don't get 0.5, somebody lied. You don't know who, but you know someone did. And so that's what this problem is asking. That's just the application, is to double check that the physics line up with the story. And so we figure out that the actual position of the wreck, through just measurement, is 0.5 miles from the station. We have a station. Oops. So we have our station. Now we know that 0.5 miles away is where the train crash happened. And so let's label 0.5 down here at the end. This is where the trains crashed. And so I'm just going to draw two objects. You can do like a P and an F, just to represent passenger and freight train. Now, we see that it says the station master claims that she noted the freight train was behind schedule. So that freight train was too far back, and that's where that passenger train caught up and crashed into it. And so it says, as regulations require, she switched on a warning light just as the last car, the freight train, passed her. So we are at this very instant where the problem starts. She has just switched on a warning light. We don't know where that warning light is yet, but we do know the last car of the freight train just passed her. You can say she is like right here. And so this is the freight train. Then we say the freight train engineer says he was going 10 miles per hour. The passenger train engineer says she was going at the speed limit of 50 miles per hour when she approached the warning light. Just as she reached it, just as she hit that point of the warning light, she saw it turn on and she immediately braked. So how do we know where the warning light is? Well, the next point says the train reaches the warning light 2 miles before it gets to the station. And so we can draw a little warning light. You can draw the passenger train just barely hitting it. Whoops. And we know that this is 2 miles. Now, we have a little width here. And so we have to think, should that be there? Well, we're never really given a width of the station. We're only really told it happens 0.5 miles later. And so in reality, this 0.5 isn't from that back edge of the station. It is from the leading edge of the station. And that is just because at the instant it starts, that the problem starts, this is our situation, and we have an origin, 0, 0. And a lot of this data is typically just going to be given to you as relative to the origin. 0.5 miles past that point, 2 miles before that point. And so you're not really going to have to assume the length of the station. That's never really going to happen. So we can only really work with what we know. We also know passenger train said she was going 50 miles per hour. And so the last bullet point, the passenger train's brakes slow it down at 1 mile per hour for each minute they're applied. So that is a -1. We are slowing down to the left. We chose our negative x and our positive x. There's customary positive to the right. We have this -1 mile per hour per minute. If you notice, we've got a sort of discontinuity between the hours and the minutes. Normally, it's like meters per second squared. It's the same time unit. So we really just want to immediately get rid of that. Get rid of that minutes. Because otherwise we might forget. We might use the wrong acceleration value. So how do we get rid of minutes? Well, we're doing some unit conversion. We need minutes to be in the top for it to cancel out. We want to convert to hours. So we think, how many hours? Well, 1 hour is 60 minutes. And so we end up with -60 miles per hour squared. And that is our acceleration value we can use in our kinematic equations. So how do we verify the position of the crash is 0.5 miles away? How can we verify that? How can we find this number? Remember, we cannot use 0.5 meters in any of our calculations because that's the number we're trying to verify. We have to use everything else we're given to find a new distance value. So if 0.5 meters, if we can't use that, what else can we figure out from this T final kind of condition? At the final instant, they crashed. That means that the position of the passenger train is equal to the position of the freight train. They're in the same spot. They're on top of each other. So we can draw this correlation, this relationship between the passenger train and the freight train. And so now that we've related their position, well, can we find an expression for their position? Again, using one of our kinematic equations, which is position of the object is initial position plus initial velocity plus 1/2 at squared. All right, so we know our initial position to be, our position of the passenger train. We know the initial position. Well, if this is our origin 0, 0, it's -2 because it's to the left. We know that the passenger train starts with an initial velocity of 50 times time, and that's plus 1/2. Acceleration, well, we found -60 miles per hour squared. And to make sure, you've got to use that -60. You can't use -1. And that is multiplied by t squared. Now, after the passenger train, we can figure out an equation to describe the freight train. And we're using the same general form of the equation, just different values now. And so x of 0 for the freight train, well, when the problem starts, initial position, well, he's at 0, 0. So that's just 0. Plus his initial velocity of 10 times t, and plus 1/2. His acceleration, he's not accelerating, right? He's not slowing down, he's not speeding up. That's just 0, t squared. And so we end up with x of p and x of f. X of f can be simplified down, just getting rid of those 0 terms to just 10t. Now, if you remember back where we first started over here, we said that the position of both trains was equal at the final instant, at t final. It's important to note that this is only at t final. We don't know what t final is, but if we make them equal to each other, we have to be really clear that x sub p equals x sub f at, terrible at sign, at t final. So we have to do the -2 plus 50t. We can simplify 1/2 times -60 to -30 t squared. This is just the equation of the passenger train's position. And this is equal to the freight train's position equation, just 10t. And so this is a quadratic that we're going to have to solve. So we really want to set it equal to 0. So just take 10t off from both sides. Get some more space. And we end up solving -30 t squared plus 40 t minus 2 equals 0. So now we can find the time it took. And we find t to be 0.052 hours. Remember, our units here are hours, because everywhere else in this problem, every other value was meters, or sorry, miles, was miles and hours. So we have to make sure that everywhere we put a time, it's going to be in hours now instead of seconds or minutes like you normally would work with. So it's really important to just make that note. So we know how long it took. Well, how do we know how far the train crash would have been? If we know how long it took, well, we could take t final and plug it into either one of these two equations, for the passenger train or the freight train. If you have to choose which one to put it into, well, the freight train's equation is much simpler. Position of the freight train at t final is just 10 times 0.052. And so we just move that decimal point in place. We end up with 0.52 miles. So the final position of the freight train was 0.52 miles according to their stories. Now this is not exactly 0.5 miles. So you might think, oh, they lied because, it's actually a little bit further. But this is within our sort of realm of error. We know we're probably not going to get a very exact answer. We can't expect that we're going to get zero point 0.5 on the dot because in reality, there's a lot of unknowns like response times and maybe they weren't going exactly the right speeds. And so you end up with a little bit of variability, but it is just 0.02 off, and so it's very, very close. And so you know that none of them were lying. They were all telling the truth, and it is not their fault. It is the fault of the track designer. All right.